Okay, hello again, everybody. Today we're going to get into Sonorant acoustics, or sort of the acoustics of the other sonorants we haven't talked about so far. So we've learned about nasals. We're going to talk about laterals a little bit today, and also a little bit about approximants and the transition cues we get for different stop places of articulation. And that's going to lead us into an initial discussion of categorical perception, and that will next time lead us into a broader theory of speech perception called motor theory, the motor theory of speech perception. So with that in mind, you should not be watching this video or following these lecture notes unless you have already done this perception experiment at home, which I'm assuming will work okay. But this is the speech perception experiment where there are two tasks where you listen to 22 different stimuli and you have to decide whether each one is the syllable ba, da, or ga. There are no other options besides those three. And then after that, there are 40 different pairs of stimuli where you have to simply decide whether each pair is the same or different. So I've posted this to the course website. You can find it under the homework exercises tab. So it's down here. This perception experiment, or the results of it, are going to form the basis of the last homework for the class, which you can find here. I'm recording this in the summer, so so we can take a look at the homework. So the homework itself is based on the results you get for the speech perception experiment, and this is also based on the results I've gotten from this experiment over the past 13 years of teaching this class. So once you guys send in your results for this speech perception experiment to me, then I will include them into these data tables, and you will use that as the basis for doing this homework. But I'll explain more about what this means by the end of the lecture today. I'm going to record another video right after this to kind of walk you through the homework. But the point is, so another point of the homework is that it kind of asks you to compare how people do when they have or have not done this experiment before. And there might be a few of you still left out there who have done the experiment before, so we can kind of add to those numbers too. But don't do the experiment ahead of time if you have not already, please, because that kind of would mess with the results a little bit. So do the experiment, then watch this video, and it will make more sense. And I'm also going to help it make more sense when I walk you through the homework at the end of this video too. So it will make sense in the future, and hopefully it already makes sense now. But if it doesn't, again, you can rewind and watch that part of the video again, or ask me questions, either in the comments or just by email. With no further ado, let's talk about the acoustics of other sonorants like laterals. So we've talked about laterals before. We discussed them in 341 to some extent. So laterals are produced by constricting the sides of the tongue toward the center of the mouth. That's why they're called laterals, right? Because air is able to flow out the sides of the mouth on either side of the tongue. Lateral just means sides in Latin. And so this is the way they work in a variety of different languages. I've got some stylized palindromes here from both German and Chinese. So in German, there's the lateral L, and you make contact here at the front of your mouth, an alveolar lateral, and then you don't have contact on the sides. It works the same way in Chinese. There's just a little bit more contact here for some reason I'm not entirely aware of. We can contrast that with a stop articulation where you have complete contact all the way around the sides in both languages, and of course we have stops in many different languages. But that's just the main difference, is that with laterals, air can pass out through the sides, or there are some cases where, and this may vary from speaker to speaker or from language to language, where you can simply make complete closure on one side of the mouth and let air flow out the other side of the mouth, and it doesn't really matter which side it's going out. But as long as it can get out of one side of the mouth okay, it's still going to sound like a lateral. I actually first kind of found this out, or confirmed it, with the first palatography demo I did for 441. This is way back in 2008. And we had a speaker of a language. It was a South Asian language. I can no longer remember exactly which one it was, but it was cool. And I should have remembered which one it was, but it had 4 different places of articulation for laterals, and so we got samples of all of them. This was the articulation for the dental lateral. And it's hard to see because we didn't get the greatest pictures of this either. Still learning at that point, I guess, how to do this well. But there's contact all along the side here on the left side as we're looking at it in this photograph. And then she left kind of an open passageway over here on the right to create this lateral. So that's one example of how you can produce a lateral, which is not open on both sides. Exactly. Normally, again, in 441, if I haven't mentioned this already, we do a in-class palatography demo, and I'm not entirely sure how we're going to do it in this semester. I have a feeling I might wind up recruiting my wife to help us out with that. We'll see if she's up for that or not. Otherwise, I might wind up just doing it on myself and making one of the weirdest YouTube videos ever as I sort of put black gunk on my tongue and then speak and take a picture of myself somehow. But we'll figure it out somehow so you guys get that experiment or experience. And I would encourage you as well to even give it a shot yourself in a socially distant and safe way. Because as long as you're just experimenting on yourself, you don't have to worry about the complications of what other people might or might not want you to do, I guess. Anyways, you can always learn a lot from palatography, so that's why we learn it in this class. I'll say more about that in a couple of lectures. Okay, so with no further weird digressions like that, we can talk about lateral acoustics. So when you do have a lateral in kind of the canonical sense where you're making a closure down the middle of the mouth and you're letting airflow out the sides, that central constriction is going to trap the flow of air in the same sort of way as the side branch of your mouth traps the flow of air when you're producing a nasal, where air can flow through your nose but then get stuck in the mouth. Similar things happen with laterals where air can flow out the sides, but it gets stuck right behind your tongue in the middle of your mouth. And when that happens, you're going to get antiformants in the same way as you get antiformants for nasals. So generally speaking, the acoustics of laterals will look like the acoustics of nasals. So we'll get some damping, we'll get antiformants as well, but because it's not sort of a categorical change when you're going from just a general oral or central sound to a lateral sound, that you're not going to get as much damping as you do for nasals. You're not going to get as well a clear distinction between when you go from a central sound to a lateral sound when you're looking at these things in a spectrogram. But otherwise, there are similarities, including like how to calculate what those antiformant resonances will be for a lateral. And this is so this is just kind of a general reckoning of what sort of antiformant frequencies you might be able to expect. You can kind of estimate the length of that sort of closure down the middle of your mouth to be 4 centimeters long, basically kind of from the alveolar ridge back to your uvula, more or less. So it kind of lines up with the measurements we were talking about last time for different nasal tubes when we were calculating their antiformant frequencies. So if you do that and sort of plug 4 centimeters as the distance measurement into the length of the tube in that equation that we've been using many times over in this class, you should get the first antiformant frequency to be about 2,125 hertz, more or less. And I will add to that for laterals, you will normally see a consistently low F1 of about 300 to 400 hertz, which is also fairly similar to what we saw for nasals. And not entirely clear exactly why this is the case, but you can kind of think of it a little bit in terms of perturbation theory, where you're making a closure sort of closer to the front of the mouth, and we have the velocity antinode there, so that should lower F1 to some extent. So it's going to be lower than what we would normally see for the formant frequencies for like a schwa. Otherwise, this is going to be similar to a vocalic articulation, right? So the overall pattern we see for laterals will look fairly similar to a vowel with some of the damping and antiformants kicked in. So I've got an example here from the language Midwagi, and I can't remember exactly where Midwagi is spoken. I think it might be in the South Pacific somewhere, but this is what this guy has to say. Alala. I'll turn that up a little bit. Alala. That's a little too much. You can see here we've got our clear vocalic segments for the ahs, even though this is a bit of a noisy recording, but here are the L's in the middle. So these are ahs are actually a little bit close to schwas because these first two formants are separated a little bit. So maybe more like fronted ah, alala, alala, which is why I'm using the script A character here. And these are the L's. So you can see the F1 for the L and then the F2 here, but the F2 is kind of getting into that anti-formant space for a lateral closure. Where you kind of really see the effect of the anti-formant is here, where you'd expect it to be around 2100 hertz, where it's sucking out that energy. And this is, I guess, a little bit in the tails of that anti-formant. So this is damped out a little bit. You can also see the bandwidth is a little broader here as well for both of these formants compared to what we see for the vocalic formants. But otherwise, this is a kind of rare example where it's nice and clear, where you go from the vowels to the laterals. There's kind of a clear break between them. It's normally not that nice for laterals, but that's why I picked this example, is because you can see it pretty easily. Another issue you get with laterals in English is that they're often velarized, kind of depending on the dialect, the phonological context, and also the speaker. So L, the way I produce it normally, is going to be velarized, which means that the back of the tongue is going to be raised as it's produced. We call this a dark L for like sound symbolic reasons, and it's symbolized as an L with a little tilde between it. Or in the middle of it. So if you remember going back to perturbation theory, we determined that kind of the second time we walked through the principles of perturbation theory that there's an antinode for F2 in the velar region, which is why you often get sort of coordination between labial and velar gestures in the production of vowels. They both lower F1 and F2. F2, I guess, a little bit more than F1. So what's going to happen with a velarized L is we should see lower F2 than we do when it's not velarized or when it's a clear L. Excuse me. Yeah. So here is what we just heard. Alala. And here's me saying this sequence. La, la, la. Yeah, with a little bit of creaky voice at the tail end. So you can see this distinction pretty nicely here. Here's my F1 and my F2 for the velarized L's. They're both low here, and they're both kind of weak in intensity. But crucially, the F2 is lower for me than it is for a clear L that we see in this speaker's production of. Alala. So that's going to go down because of that velarization. And as we have talked about before, this pattern can make an L or an ol sound like a high back vowel because it has low F1 and low F2, and they're also weaker in intensity because it's a lateral. And as we know, high back rounded vowels tend to be weaker in intensity because of the lip rounding on top of them. So in theory, these could be confused with high back rounded vowels. Sometimes they switch back and forth in phonology. And I thought I had something more to say about that, but I guess I don't. You can also kind of confuse them or can easily confuse them if you're looking at these in spectrograms, where this might look like an oo or an o to you. So just watch out for that, I guess, is all I have to say. There's a reason for it. Laterals are usually more intense than nasals. Like I said, there are similarities between the two, but laterals do have sort of more airflow coming through the mouth. There's less damping because you're not closing off that mouth closure completely. There's also kind of less volume and less surface area in the part of your vocal tract that is doing the damping, so not as much energy can get sucked out. And then kind of this troublesome fact that I alluded to a while back, which is that there is not as clear of a break between vowels and laterals as there is between vowels and nasals normally. So as long as this vowel is not super nasalized going into an articulation like Anna, you will see a nice kind of clear break between when you go from the vowel to the nasal, because that's the point at which your velum comes down and opens that passageway through your nose. With a lateral, you're making that lateral closure, maybe bringing the tip of your tongue up to the alveolar ridge or your upper teeth, but you're still leaving the sides of the mouth open, so it's kind of just a partial closure, and you don't get that sort of strong distinction between the two types of segments. Yeah, and then it comes back again. So it's not, a kind of common task in phonetic research is to go through a series of productions that some speakers have made and that you've recorded, and to kind of segment them to sort of pick out the parts that you want to look at. So with this, it would be super simple to say, well, here's where the N begins, here's where the N ends. For the ol, you kind of have to say, somewhere in here it begins and somewhere in here it ends as well. It's more gradient than that. But otherwise, there are similarities between the two. You might as well notice, again, since I am velarizing this guy, the F2 dips down. So F2 is relatively low for an ah, but for the ol, it's going to be even lower. And it doesn't really dip down here for the N, right? And then here's my sort of anti-formant frequency for the L up here around 2000 hertz. You can also kind of compare ol and
Alla, ara.
And I guess I'll mention here, I initially transcribed these with an ah because that was what I was targeting, but when I actually say them, it kind of becomes more like a wedge.
Alla, ara.
Just so you know, I'm not like trying to pull one over on you. But the big difference between ol and will tend to have more intensity as well than an ol. There's less kind of damping over R overall with R because you are not really closing off the vocal tract that much. Maybe you make contact with the sides of your tongue on your teeth, but air can still flow through the middle of your mouth. And then, of course, has a low F3, right? And we can see this jumping down quite nicely here. Dipping down, I guess is what I was trying to say. F3 for ol stays put, maybe goes up even a little bit higher, but it's F2 that comes down for ol.
Alla, ara.
So even though these two sounds also have a habit in phonology of kind of going back and forth with one another or having some sort of underlying phonological relationship with each other, they're fairly different acoustically speaking. So it's a little bit of mystery why the liquids kind of form a natural class like that, but they do. I'll leave that up to further research that you might want to do in order to figure out exactly why. Okay, so that's all I'm going to say about laterals. Glides are vowel-like sonorants, which are going to, in some cases, look a little bit like what we see for laterals and nasals, but basically they have less constriction than either of those types of segments. So they're getting closer and closer to vowels here, and therefore their acoustic signature is going to look even more like vowels than either laterals or nasals do. The difference between glides and vowels, there's a couple differences. One is that with glides you get slightly more constriction than a vowel at the same place in our articulation. Each glide is going to correspond to a different high vowel. So you can kind of describe them as either vowels on the one hand or consonants on the other. So take the vowel E, it kind of corresponds to the glide yod. This is Peter Latefoged saying
Yeah. Yeah.
Maybe I can make that louder.
Yeah.
So if it's a vowel, it's a high vowel. All these are going to be high vowels, but it's front and unrounded. And since it's high and front and not rounded, it qualifies as a palatal glide.
Yeah.
Yeah. So you say E, and then if you push your tongue up a little bit closer to your palate, and then make that articulation just kind of not last very long. It's sort of a transient sort of articulation, which is why it's called a glide. You get a yod as opposed to an E, which you can hold forever. Similarly, we have the high back rounded vowel oo, and that corresponds to the labial velar glide. So it's labial because it's rounded, it's velar because it's back. Here the palatal is front and it's unrounded, so we don't have to say anything about what the lips are doing. But basically there's a two-feature system distinguishing these vowels, whether it's front and back or back, and whether it's unrounded or rounded. And because there's 2 features with 2 specifications each, that means we can get 4 different possible glides to correspond to the 4 different possible vowels with those features. So a labial palatal glide is front and rounded as a vowel, and it is symbolized as a vowel as this lowercase u, and then as a glide it's this upside down h, which I'm kind of competent at producing, but we get this sound in French if you have studied French at all, and a sound that I wouldn't really trust myself to produce that well, and in fact I don't really trust Peter Laterals to do it either, but he tries here in this example, is the glide that corresponds to the back unrounded vowel, this guy, which we get in a language like Japanese, and if it's a glide, it's the same sort of upside down M symbol, or if you think of that as like a rounded W or something, with this little tail on the right hand side. So something like agua, agua. It's always difficult to produce those back vowels without wanting to get your lips involved too. That's ideally how it's supposed to be pronounced, as a velar glide. Okay, we've seen those before, so hopefully that's not too much of a surprise. What I want to add to this, again, is that each glide's acoustics is going to be similar to those of the vowel that they correspond to. And we should know what the acoustics of these vowels look like, or know what to expect, because we've talked about the acoustics of vowels at some length already in this class, right? So yeah, glides look like high vowels, but they're shorter than vowels. Like I said, they're kind of transient articulations. They also tend to lack steady states and exhibit rapid transitions into or from the vowels. That's kind of why they're called glides. They will be lower in intensity than vowels because you're making slightly more of a constriction when you produce them than when you produce a high vowel. They're a little bit more consonantal in that sense. And you'll also see this most particularly in the higher formants of the glide articulation, or the acoustic signature of the glide. Yeah, so I can give you a few examples. This is me trying to produce sort of the corresponding sequences of the relevant places of articulation here, of going from like a vowel to a high vowel to another ah at the end, and this is with a glide rather than a vowel in the middle. So we should see the formants basically doing the same thing for both of these articulations, but this one's going to go by more quickly. Yeah, so not that normal of a thing to say, but it works for this little demo. Right. So this one is going by more quickly. It's a little bit hard to see that here because I kind of made the spectrograms the same width on the slide. But you can see down here, this one's a lot longer in time. It's 0.78 seconds, and this one is 0.53 seconds. But the main thing is, for both of these guys, F1 goes down. That makes it a high vowel, or a glide. And F2 goes up. So that's what makes this an E rather than a different kind of high vowel. And you can also see that the formants kind of fade out here in the higher range. Like I said, with glides, you tend to get lower intensity in the higher formants. Yeah. We see the same sort of pattern with high back rounded vowel, or a labial velar glide. Yeah. Right. So with this guy, we should see the same formant pattern we see with an U, which is where F1 and F2 will both go down. And also we see a lessening in the intensity of these higher formants. Again, you kind of have to intuit infer the shortness of the glide here, because the overall spectrogram is shorter in the glide case than it is for the vowel case down here. And I get some nice creaky voice here at the tail end, but what else do you expect? Yeah, so you can also get a closer look, or maybe a clearer look, at how that intensity fades out at the high end of the frequency scale, just by going from a vowel to a glide to a vowel at the same place of articulation. And during the glide articulation, you see that fade out of sort of the narrower constriction when you produce it. Sorry. Or, I did it again. Yeah, so there's less intensity here in the middle, and then the formants just kind of come back in the same place on either side of that glide articulation. But F1 goes down here for this guy. F2 goes up, or it stays relatively at the same space at the high end of where we expect F2 to be. F2 is going to be low here for the high back rounded vowels, or the labiovelar glides. And then there's these where you see that where the formant switch going from sort of front to back in these, or back to front in these articulations.
We.
Or
you.
Both pronouns in English. But as you know, I like to make the joke that this is what it sounds like when I go on a roller coaster ride.
We.
Yeah, pretty exciting.
You.
Okay, still excited. But going from back articulation to a front, F2 is going to go up. And we're also unrounding lips to get to, starting with a rounded lip articulation, going to an unrounded lip articulation. The opposite sorts of articulations here will lower F2 as we go into from the palatal glide to the oo. And in both cases, you should be able to see there's less intensity here during the glide as well. But like I said, it doesn't stick around, right? So most of the information you get about it is in the changes of the formants. And that leads me to a discussion of transitions. So we've seen these before in 341. It's worth going over them again because they're important. Much of the meaning we get out of speech when we listen to it or try to perceive what's going on in it comes to us through the changes in the speech signal. So when stops are released, they go through a rapid period of change, and they go through their formants, or the formants that will emerge in the spectrogram during that sort of production will undergo a transition phase in between the stop and the vowel. So you can think about this if you have a stop closure, like closing your two lips for a buh, and then you open them. The first thing you're going to get after the closure is probably a very short release burst where kind of there's a puff of air that pops out of the hitherto tightly closed chamber of air in your mouth. So there's a little pop. And then you get a glide-like transition as you keep opening your mouth to get to whatever vowel you're trying to target after the stop. And once you finally get there, you'll get, for at least a little bit of time, some sort of steady-state vowel where you're not going to be changing the articulatory shape of your vocal tract, and you'll produce formant frequencies at a relatively steady set of frequencies for a while. And we call that a steady-state vowel in sort of the idealized case. What we want to kind of focus on today, though, is this third step, not necessarily the release burst or the vowel, but rather the transition between those two stages. And if you have this whole process go in reverse and you go from a vowel to a stop articulation, you get the same sort of changes in reverse, but you will not necessarily get a release burst, and you'll definitely not get a release burst as you close the vocal tract. You'll just get steady state vowel, transition, and then a stop closure. And then maybe when you open your mouth up again, you might get a release burst afterwards, but it's not in between the transition and the closure because no pressure is built up at that point in time, right? At least not in your mouth. So the other part of this is that when you make that transition from the vowel to the stop, going kind of in reverse, is that usually those transitions are a little bit slower. And they take more time than when you're opening up your mouth. That's simply the way that people typically articulate these things. So that's interesting because these transitions can give us cues to the place of articulation of a stop, which is not always easy to pick up. Because they go by more quickly when you open up your stop closure, they're kind of less reliable, it's harder to pick up information in them when you're opening up stop closure quickly. So often you get more information about where the mouth is headed in a vowel to stop transition when you're closing your mouth as opposed to opening it, because it just gives you more information over time. It's easier to perceive. So I'll give you examples of both of those things here from this Armenian word,
bug,
which has a bilabial stop at the beginning and a velar stop at the tail end. And so we can see kind of the various stages here. This is closure voicing during the initial stop, voiced stop, the bilabial B.
bug.
And again, this is not the greatest recording. I need to get Mouche, one of our professors here in the School of LLC, who's from Armenia and can produce this without the noise in the background, to record these for me in the booth once we finally get access to university again. Sorry about the tangent.
Bug.
You should be able to hear that closure voicing a little bit as he produces this stop at the beginning of this word. It's a little harder to hear the release burst here because it's so weak. Generally, bilabial release bursts are not super strong, and they're often weaker even when you produce the stop with voicing because less pressure kind of builds up in that case. But what we see here is in the middle, there's a steady state vowel. It's hard to pick up on the transitions here at the beginning, but you see them better here at the tail end. Like I said, they take a little bit more time as you're closing your mouth. So moving into the G, we see these nice formant transitions where F2 goes up, F3 goes down. They kind of come together.
Bug.
And we get another stop closure at the end with voicing in the middle too. So that's why we have this low frequency hum at the end there. And at the very end, we get a nice clear stop release burst, which is not always the case, but it is in these Armenian examples, and you can hear it.
Bug.
That little at the tail end, with a couple of different openings as we walk through the opening of the mouth here. A couple of different release bursts. Okay, so that's what we can see in a spectrogram. And again, just to remind you, when we talk about formant transitions, what we're talking about are these changes in the frequency of formants as we go through some speech articulation. Okay, so one of the reasons why I'm talking about this is because this was a bit of a surprising finding in the history of phonetics that formant transitions were such an important cue in speech to listeners. So when the spectrogram was first invented, like I said, in World War II, and then after that, people started playing around with it in the late 40s and early 50s, it was pretty easy or relatively easy to figure out how to identify vowels from their spectral characteristics. And that's why we talk about vowels first when we walk through acoustic phonetics. It's just they're the easiest segment to kind of figure out how they work. But it was a lot harder to figure out how the acoustics of stops and stop place of articulation worked, because they didn't seem to be nearly as consistent as vowels, and they also had cues that went by really quickly, right? So there's a lot going on. And like I said, eventually researchers realized that the formant transitions are really useful in these cases. Like I said, we get a lot of information in speech out of the changes that are produced in speech, the acoustic changes that happen. So the formant transitions between vowels and stops can provide a reliable cue to place of articulation. I've got this question here, why? I will let you think about this question here for about 5 or 10 seconds. Why might it be important that why might these changes be important? What could they possibly signal to us if we're listening to speech? How are they produced is one way to possibly think about that. And maybe you can kind of compare how you might get formant transitions as opposed to how you might get the formant values for vowels specifically. The answer I'll give you is that the resonant frequencies of the vocal tract change as stop gestures enter or exit the closure phase. And the way they're going to change, they're going to start to point to what the vowel formant frequencies would normally be if you produced a vowel in the same place of articulation, but with just more constriction, right, as you're going from a vowel to a stop. So to give you an example, what I mean by that, normally when we look at vowel transitions going into bilabial stops, we see those formants going down into the closure phase of a bilabial stop. So going back again to perturbation theory, normally speaking, we have, or just always speaking, we have velocity antinodes for all formants at the lips. So if you make a constriction at the lips, then those formant frequencies should go down. If you are making a bilabial stop closure, you're making kind of an extreme constriction at that particular antinode for velocity. You're making it so that it becomes completely closed. You will get the same acoustic effects that you will decrease the formant frequencies at that place of articulation. So that those changes kind of are like pointers saying, well, here's where the constriction is being made. for listeners to kind of pick up on. If all the formants are going down, that's a good cue that we're making a stop closure at the lips.
Baby.
Yeah, that's me trying to say that word.
Baby.
Without any creaky voice. So my B at the beginning is actually unvoiced because I'm not a speaker of Armenian. The one in the middle is voiced because it's in between two vowels. And that's where we can kind of see this pattern the most clearly, where especially F2 and F3 are going down into this bilabial stop closure here in the middle of this articulation.
Baby.
Yeah, that's the easiest case. Unfortunately, the other stop places of articulation don't work quite that simply. But here I've got arrows pointing out the formant transitions. I'm also going to point out here that formant transitions for stops or going into or out of stops are usually going to be a lot more quick. They're going to go by a lot more rapidly than what we see for glide places of glide articulations.
Baby. Wave.
So this is going to look a little bit like that wee example we saw a few minutes ago for the wave, where we have low F1 and F2 for the glide articulation, and then because we're moving to a front vowel, F2 is going to go up. This also puts us into a front vowel for baby, in fact the same vowel.
Baby.
But this goes by really quickly, going from a B into that articulation. And in fact, the kind of extent of the formant transition is not nearly as large as it is for the glide articulation as well. There's just a little bit of a formant movement up here. But it's in the same direction, and it goes by more quickly than it does for the labial-velar glide at the beginning of
wave.
Yeah. But basically, F2... or these higher formants are going to go down into labial-velar glides. They're going to go down into bilabial stops as well because we have a velocity antinode at the lips. It's just that these are going to move a little more slowly. That's just how we articulate them as compared to going from a stop to a vowel. Yeah. Like I said, though, for other places of articulation, the formant transition story is more complex. So we can start off with alveolars. From the way that alveolar transitions work, and I cannot say that word today, I don't know why. The way that alveolar transitions work is that from front vowels into alveolars, F2 tends to slope downwards. So I think you can also get here as well from perturbation theory. So you might recall that we have a velocity antinode for F1 at the lips, and we have a velocity antinode for F2 at the lips and F1, and we have a velocity node for F2 at the palate, right? So if we constrict at an antinode, the formant frequency should go down. If we constrict at a node, the formant frequency should go up. Alveolars are kind of somewhere in between your lips and the palate, maybe a little bit closer to that node at the palate. So F2 will go up a little bit from its default value of like 1500 hertz for a speaker like me. But it's not going to go up that much. So compared to like a palatal place of articulation, which is what we normally get for like front vowels, it's not going to raise F2 as much. So when you go from front vowels into alveolars, F2 will tend to slope downwards. Conversely, back vowels, if you think of these as velar articulations, and you think that, well, there's a velocity antinode for F2 at the velar place of articulation, so that will lower F2. And if the back vowels are lowering F2 and an alveolar articulation is raising F2 a little bit, so F2 should go up if you go from a back vowel articulation into an alveolar stop. That's why we're kind of getting these two patterns here. Overall, what we wind up, and that explains why. Overall, what we wind up seeing is that F2 is going to kind of point to around 1650, 1700 hertz on the frequency scale when we go into an alveolar closure. And you can kind of see this relatively well in these examples here. This is Bruce Hayes producing all four of these vowels in an H vowel D context.
Heed. Hid. Head. Had.
So from an E, which is going to give you the highest F2, that is going to move down a little bit going into the alveolar stop here at the end. We see it a little bit better for the hid,
hid,
because the vowel formants are just not going to be as steady for a lax vowel like I,
hid,
or similarly for E, which is pretty close to a neutral vowel or like a schwa.
head,
You can kind of see this F2 pointing to around 1700 hertz. I think this example here
had,
is nice because it goes from like an A at the beginning, and then there's kind of a schwa phase at the tail end of this, because lax vowels like to do that in English. They like to go from a lax vowel to a schwa.
had,
Maybe more in Southern American English than in the variety that Bruce Hayes speaks, but
had,
it goes down for F2, and then it actually jumps up a little bit because an alveolar closure is going to lift up F2 a bit compared to its default value for schwa, which is why you get this overall pattern.
had,
But in each one of these, more or less, this F2 formant is pointing more or less to 1700 hertz on the frequency scale. It doesn't get there quite as much in this one
heed,
because F2 is really high to begin with for the E, but generally that's where it wants to be. And you can also see that a little bit at the end when he releases these Ds. You're getting what looks like a formant here on the other side of the release burst, right around 1700 hertz or so. And like I said, if you're producing a back vowel, your F2 is going to be a lot lower than 1700 hertz. It should be lower than 1500 hertz. So we should see F2 rising up into these alveolar closures every single time.
hod, hod, hood, hood,
Hood is kind of a funny one. Hood.
hood,
The is another lax vowel and doesn't really want to stay put there. So it kind of rises up into something more like an I before he actually gets to the stop closure at the tail end.
hood, hod, hod, hood,
But each one of these, and also the kind of phantom formant you get here after the release of the stop, is at around 1700 hertz or so on the frequency scale. So that's relatively nice in terms of its reliability, that we have kind of one frequency we can rely on. It's just not as simple as what we get for bilabials, where the formant frequencies are always going down into the stop. Yeah, so this restates that point that I've mentioned already several times over. This apparent frequency value that we get for alveolars is called the locus of the formant transition. It's kind of where that transition begins or ends as we go into the stop. And like I said, back in the 50s, when people were still trying to figure out how these acoustic cues work, and okay, we're still trying to figure out how the acoustic cues work, but one of the first insights they had is that you could simply get a percept of how where stops are based on the formant transitions alone. So I've got some examples here. Somebody just kicked up a chainsaw out there, but hopefully you don't hear that. I want you to listen to these, and you can let me know, or you can let yourself know in the privacy of your own home what you hear in these. But what I've got are three articulations by myself where they're stop, vowel, stop, but I've removed the stops around the vowel, and I'm just giving you the vowel along with its transitions into or out of the stops on either side. Can you tell me what stops I was producing?
dog, dog, gob, gob, bod, bod,
Okay, so the vowel in the middle is always that ah vowel. You might have picked this one up. I know they go by pretty quickly,
dog,
but that was originally a dog articulation.
dog,
D-O-G, this one,
gob,
is not really a high frequency word, nor is this one.
bod,
But this one is G-O-B,
gob,
like great gobs of goo or whatever.
bod,
And this is B-O-D,
bod,
B-A-D, like, you know, somebody's body or what have you. So I don't know if you got those perfectly,
dog,
but
gob,
when you know them,
bod,
I think you can hear that pretty well. But you're not hearing any stops. You're just hearing the vowel and kind of the edges of the vowel as they go into or out of the stops on the sides. The one catch with this, so alveolar transitions are more complicated than bilabial transitions, and it turns out that velars are even more complicated for interesting reasons. So velar formant transitions do not have a reliable locus frequency for F2, and one of the reasons is that velars exhibit a lot of co-articulation with neighboring vowels. So this is a fact about English. in one sense, you could kind of think about this as, well, maybe we shouldn't describe this whole category as velars. Rather talk about them as maybe front velars and back velars, because when you're producing a velar stop next to a front vowel, it becomes more of a palatal stop, and you get a higher, you'd expect a higher locus in that case because we're nearer to a node for F2. But the more velar they are, the more you expect them to have be close to that antinode for F2 in the velar region, and so you'd expect the locus to be lower. So we're kind of dealing with two different sets of stops here. What we do often see, though, with velar transitions in English, 1 out of 10, is that F2 and F3 come together in what we know as a velar pinch. And this we have already seen in the initial Armenian articulation that I showed you at the beginning of this lecture,
bug,
or a few slides ago at least,
bug,
where F2 goes up and F3 comes down, and they kind of get pinched together to let us know that we have a velar stop here at the end. And I've mentioned this before in 341, but when you look at the release burst for a velar stop, you tend to see more intensity in that same region, like around 1900 or 2000 hertz, for the release burst as the same place where the F2 and F3 come together.
bug,
That's just sort of the frequency range at which the vocal tract resonates best when you make when you're becoming close to a velar articulation.
bug,
Same thing with the voiceless one here. We just don't get the closure voicing in this particular case. We see the release burst a little bit more clearly here because normally release bursts are stronger for a voiceless stop.
bug,
You can kind of get more pressure to build up behind them before you release them. But the same idea. Yeah, I think because that guy's really going after that tree right now. Yeah, actually, I'll walk you through these and then pause and close the window. But this is the point I was trying to make about velars, is that sometimes they're not velars, they're more like palatals. So I've got myself producing voiceless velar stops here in 3 different vowel contexts. This is me saying
key,
and,
caw,
and.
coo,
And I've also got mid-sagittal diagrams of my or somebody's tongue as they produce similar sorts of articulations. For a key articulation, you'd expect the vowel to be a little bit fronter here, closer to where you want the tongue to be for an E right after it. For oo right after it,
coo,
your tongue might be a little bit further back because that's a backer vowel. And then for an ah, you want to get down here to a pharyngeal constriction right afterwards.
caw,
So this one's going to be pretty far back as well, maybe even further back in like an uvular stop in this case. And so these all get processed, if you're a native English speaker or listener, these all get processed in your mind as a K.
key, caw, coo,
But if you listen really closely, you can hear the distinction between them, or you can hear subtle differences between them.
key, caw, coo,
And to kind of help magnify those for you, I'll play just the release bursts by themselves without the vowel after them. And the sort of vowel flavoring of the release burst should jump out at you. Yeah, it's not going to work. We'll try it this way. Yeah, so you can kind of hear this one has an E right after that, even though that's only the release burst itself. And this is getting ridiculous with the chainsaw, so I'm going to stop now, and then I'm going to pick back up at this point when I come back to part number 2 of this video. So I'll see you in a minute.